quite often we just simply rely on the gas gauges here to analyze our data. Well, that works fine, but there are some other things that are available, and if you want to know what the full suite of tools is, let's take a look at that. Here's your analysis of variance table, or your ANOVA table. Things that you ought to notice there are F values. That's a signal to noise ratio. That is the amount of variation your variable can account for, divided by the random noise that's left over when everything you can do is subtracted out. Typically, if you're in the high single digits here, you're going to have a significant p-value. Variance inflation factor tells you if you've got one or more variables in the input that are really each other, only in a different set of clothes. And if your VIF is up above 1.5, you're probably feeling some strain, and at 2 you've got problems. And the p-value is, of course, the probability of being wrong if you assert that this variable makes a difference. R squared adjusted, this is derated R squared, adjusting for degrees of freedom. And epsilon squared is a very aggressively conservative measure of how much variation you're explaining. If variation is showing up, the same variation is showing up attached to more than one variable, it just takes all of it out. So if your epsilon squared is sinking compared to your R squared, you've got a problem with multicollinearity, or input variables really being the same as each other. S is the standard deviation of the data points around your trend line. Of course, in other videos we've talked about Levene's, Bartlett's, and F, and then here's an equation of state. So you can just plug in your X values in that and get a value of Y for any combination you like. This is the equation that the optimize function works off of. Generally, the rule then is we work from left to right along these buttons. Residuals, we'd like to see our residuals versus fits and our residuals versus run order be within the control limits and have no obvious patterns. We'd like to see them be normally distributed. That means that we've sucked out all of the information that's in the data. And this is what the non-normal slider works off of when you're testing your assumptions. You can look at your effects plot, and we have not allowed interaction, so these are grayed out, and these are the effects of temperature, water, and soil type. Sometimes it's better to look at that, in fact often it's better to look at that in a scatter plot, and it's really kind of nice. You can lasso a set of points here, and those same points that you have lassoed will then pop up in blue in the other diagrams, and that's very handy. ANOM we're going to skip. The optimizer function, I can drag these and predict what my harvest weight is as I adjust these input variables. Soil type is categorical, so I can only drag that from one dot to another. The other thing that I can do is I can put in spec limits, which is really kind of interesting. Let's do that and click calculate. And then in addition to getting some kind of an estimate of our output variable, I also get CP and CPK. Very, very useful. So that's how you do the advanced analysis.